Hello everybody, lecture 4. Now I explain for you more information about metals. We already know that there are several types of ferrous metals, and the best known are steel, wrought iron, cast iron, and stainless steel, of which ordinary steel is the most important in terms of usage and application. Essentially, steels are iron carbon alloys that may contain other alloying elements. In fact, it's possible to have thousands of different types of steels with different chemical composition. As we shall see, later the mechanical properties of steel are sensitive to the addition of minute amount of carbon, which is usually less than 1%. Such steels are often referred to as plain carbon steels. In general, many common steels are categorized in accordance with their carbon content, namely low, medium, and high carbon types, as discussed later. As there are so many different types of ferrous metals, for simplification, these have been classified in this figure. So this is a classification of ferrous alloys. It's also vitally important to grasp the chemical difference and phases that exist in ferrous alloys, namely steels and cast iron, and the iron carbide, a diagram commonly known as the ferrum 3 C phase diagram, provides the basis for understanding the chemical composition and mechanical properties of steels and cast irons. So we see that steel include low alloy and high alloy. Low alloy include low carbon, medium carbon, and high carbon, and that also include carbon. Low carbon include plain and high strength and low alloy. Medium carbon include plain and heat treatable, and high carbon include plain and tool. Steel with high alloy include tool and stainless. And about cast iron, this is a gray iron, ductile iron, white iron, and malleable iron. This is the iron carbide phase diagram showing the chemical phases that exist in steels and cast iron. As can be seen, there are many different possible combinations of steels and cast iron. The iron carbide diagram is undoubtedly the most important fast diagram in metallurgy. This is so as steels are the primary structural metals in practically every technological and engineering application. The possible information to be deducted deduct from this diagram is vast, primarily for metallurgists, materials scientists. Also, civil engineers and architects don't delve deeply into the metallurgical theories. It's still important to grasp the fundamental science. From the ferrum 3 carbide fast diagram, it's important to note that steels contain up to 2.1 weight% degrees. And also it's usually less than 1%. Cast iron contain 2.1, 6.67%. So most cast irons contain from 3 to 4.5%. Therefore, the chemical compositions of both steels and cast iron are almost identical. Iron plus carbon and up to a few percent. And thus it's imperative that we are able to differentiate and distinguish between the two. The fast diagram above is only a portion of the iron carbide fast diagram, which extends to 100%. However, the portion of up to 6.7% is of importance as it covers all steps and cast iron, all steels and cast iron. Given the majority of steels are as low medium carbon, at least 70% of all metals or steels used worldwide contains less than 1% carbon. In fact, in most cases less than 0.7%. At room temperature, most steels have a chemical structure of phase present called a alpha ferrite or alpha iron, which has a BBC crystal structure. This phase exists as part of alpha ferrite plus cemented. This dual phase is known as perlite, which is present in all steels and cast iron at room temperature. At 727 and before 912 degrees, the alpha ferrite transforms to gamma austenite. or alpha or gamma iron, also you can say, which has an FCC structure. However, gamma austenite starting to form alloys containing 0.76% as a phase of alpha plus gamma is present on the left hand of the phase diagram. With an increase in temperature, eventually there is a complete transformation to gamma austenite. The transformation temperature 727 up to 912, as this is dependent on the carbon content as shown on the bottom left hand side. And we can see that as we increase the carbon from 0 to 0.76 degrees with the temperature at which alpha ferrite transforms to gamma iron or austenite decreases from 912 to 727 as it follows the solid time line. As the temperature is increased further, the gamma austenite transforms to theta ferrite. And at about 1400 degrees, which has a BCC crystal structure. As the temperature reaches about 1500 degrees for steels containing up to 1 weight percent carbon, we enter the liquid phase. And thus the alloy melts at about 1500 degrees. If we now increase the carbon content to 2% above 727 degrees, the metal transforms from ferrite to gamma plus ferrum 3 carbon. Then, as the temperature is raised, there is a transformation to gamma, then to liquid plus gamma. At this stage, the metal starts to melt, and then finally to complete liquid. Cast iron have similar reactions, transformations, with the difference being that there is a larger amount of cemented present. Another important point to note from this figure, from 1.3 to 1.147 degrees. Thus, in general, cast iron have melting point which are considerably lower than steel, about 1500 degrees. Therefore, they are easily melted and amenable to casting, hence the name. There is a myriad of information which can be deducted from the iron carbide diagram. However, it's not expected that students or professionals from the civil engineering or architectural disciplines will be required to acquaint themselves with much more than the fundamentals covered in this lecture. Nevertheless, a list of indicative sources for future readings is included at the end of this lecture. Having looked at the chemical properties of ferrous alloys and more importantly that distinguish between steels and cast iron, the remainder of this section further elaborates on the different types of ferrous alloy. The following are the most common type. So, what's an alloy? An alloy is a mixture of a metal with at least one other element. Steel is a common example of an alloy. It contains iron mixed with carbon and other elements. Adding other elements to metal changes its structure and changes properties. The final alloy may have very different properties to the original metal. And what type of alloys are there? Alloys have been used for thousands of years. Bronze, an alloy of copper and tin, was commonly used by civilizations before iron extraction methods were developed. Other well-known alloys include brass, an alloy of copper and zinc. It doesn't tarnish and is used for door knobs, buttons, and musical instruments. The next, solder. An alloy of zinc and lead. It's used in electronics to attach components to circuit boards. Amalgam, an alloy of mercury and silver or tin. It's used for dental fillings because it can be shaped when warm and resists corrosion. Is gold an alloy? Also, pure gold is sometimes used in electronics. Gold jewelry is always a mixture of gold and other metals. Pure gold is actually quite soft. Adding small amount of other metals makes the gold hard enough to use in jewelry. Alloying gold with different metals also affects its color. The familiar yellow gold is an alloy of gold with copper and silver. Adding more copper than silver gives redder shades. Yellow gold. And this is a white gold. White gold is an alloy of gold with nickel, platinum, or palladium. Around 12% of people may be allergic to the nickel in white gold. So you must check this alloy and this alloy of gold if they're a nickel. When is a cover coin not a cover coin? When it's a copper coated alloy. Copper coins used to be made from pure copper, but most copper coins used around the world are now made from copper alloys. However, as the value of copper increased, the metal used to make the coin became worth more than the actual coins. And what is steel? Steel is an alloy of iron and other elements, including carbon, nickel, and chromium. Steel is stronger than pure iron and can be used for everything from saucepans to suspension bridges. And why is steel stronger than iron? The atoms in pure iron are arranged in densely packed layers. These layers can slide over each other. This makes pure iron a very soft material. The atoms of other elements are different size. When other elements are added to iron, the atoms distort the regular structure of the iron atoms. It's more difficult for the layers of iron atoms in steel to slide over each other. And so this alloy is stronger than pure iron. And what types of steel are there? Steel can contain up to 2% carbon.